Ooh.
Yeah.
Oh, you're doing it this way? Welcome to another episode. A spooky episode of Eigenbros.
Wow.
Yeah. Cue the screeching. So today it's a very spooky episode about quantum supremacy.
Indeed. So today we talked about basically what is quantum supremacy, you know, what does it mean for the future?
Yeah.
You know, we kind of went on some tangents a little bit about self-driving vehicles and other things.
Turn it back around, you know. You kind of, you know, you take a couple tangents, but you know, you get to we kind of wrapped it up a little bit nicely because I wanted to kind of ask Terence because he always had the quantum question, you know.
Yeah.
It's like, what the hell does it really mean? And I think seeing it applied definitely, it gave me an appreciation of like knowledge of quantum mechanics.
Sure, me too.
Yeah.
Me too. So hopefully this one could be educational, especially for, you know, you guys who are kind of a little bit on the fence of understanding what the heck quantum actually is.
Yeah.
So, yeah.
You can see it applied. Yeah, you can see it applied, and like, you know, we kind of, if you don't really know anything about quantum computers, I think we gave a pretty good survey.
Yeah.
Yeah. So,
Cool. So, yeah, guys, just make sure you like, subscribe, comment, share,
yes.
and check out the Twitter at Eigenbros. Check out the website, eigenbros.com.
Yes.
And that's it, guys. Stay tuned.
3, 2, 1, and we're live.
Make it so.
Fire off in the comments. Guess who I am?
And it should be obvious who I am.
It should. Maybe. You know, I mean, all I knew was Star Trek.
That's true. I need a bald head, I guess.
I was like, Star Trek.
Maybe a
okay.
little more than bald head.
You know, for me, it's pretty simple. You know, if you're a 2000s baby, I think you can figure it out, right?
I don't know. It was hard for me to guess.
Really?
Yeah. Then again, I'm a 90s baby.
What was your guess?
Gangster Teletubby?
It's not the first one. That's not the first guess I got. Because people were guessing. You're like, oh, dude, Dragon Ball Z. And I was like, no.
How's that Dragon Ball Z?
I know. I guess the outfit kind of looks, I don't know. I said, just give him the right poison for Cusco.
See, I didn't even see Emperor's New Groove.
Oh, you haven't?
No.
Dude. Patrick Warburton is great in that one. You know Patrick Warburton?
Is that Joe?
Joe
from Family Guy?
Yeah. He does a bunch of voices. I mean, he's kind of an iconic voice, right?
Yeah, he's great.
Yeah. Oh, yeah. It's all coming together.
I know that meme.
Yeah. He's great. But yeah, this is my costume. It's got the little thing on top.
Mm-hmm. The little Teletubby thing?
Yeah.
Little antenna?
Squeak, 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 squeak. He's kind of got this Ace Ventura kind of thing. I was trying to work on the impression.
Does he?
Yeah. He's kind of got this, like, you know what I mean? Like the Ace Ventura thing where he's like, oh, righty then. You know, it's kind of got that same energy.
Yeah, I guess I know what you mean. I know what you mean.
It's got
but
that
then again,
breath.
Ace Ventura's a little bit more hammed up, I feel like.
Oh, yeah.
You know, alrighty then.
Yeah. Alrighty then. Yeah, Jim Carrey. Peak Jim Carrey if you...
Yeah, Jim Carrey's great.
So what is this? So you're Luc Picard?
Jean-Luc.
Are you Jean-Luc Picard?
Mm-hmm.
Okay. See,
Although I got to admit, I'm actually more of a Voyager fan than a Next Generation fan.
This is all
New to you?
New to me.
Uncharted territory?
You know what? I tried getting into Star Trek.
But you didn't like it?
I just couldn't. I don't know. I just couldn't. I don't know what it was. Maybe I watched the shitty episodes or something.
Well, how long ago did you try to get into it?
When I was a teenager.
That might be the reason.
Yeah.
I didn't like Star Trek for most of my life until I became an adult.
Okay, so you became a science nerd.
Yeah, exactly. Well, I was already a science nerd, but I was more into like less campy or hammy shows.
Oh, okay.
And Star Trek has very much of that kind of like corny, campy feel to it.
Yeah.
But now that I'm an adult, I can appreciate that way more than I could as a teen.
Yeah.
Like I was always about, you know, cool or edgy shit.
Yeah.
You know, because I was a little edgelord. But
Yeah, I like Star Trek now because
it's got all these political themes and philosophy themes and things like that a lot of shows don't go at the same level in depth on.
Mm.
How are we looking on our recording, Juan?
That's good.
All right. Yeah, so Star Trek is interesting. I like it. Very much a fan now.
Excellent.
So you should check it out. Voyager's my favorite, but I'm watching the Next Generation right now.
Okay. That's
So,
good.
Yeah.
I mean,
Yeah.
I should probably give it a try.
You should.
Because did you ever get like the extended cable package?
Probably
Channels.
when I was a kid, yeah.
Yeah. Because I
Had
used,
like hundreds of channels.
I used to go to my friend's house to watch this one network channel, G4.
The video game one.
Yeah, the video game channel.
bro.
Yeah. They
Yeah.
they used to. That's where they showed the Star Trek. That's where they were showing it.
Oh,
Like
I didn't
the
know they showed
reruns.
Star Trek there.
Yeah. I mean, it's a gaming channel. They're like, okay, there's got to be crossover here.
I see. Nerds like this, nerds like this. You know, come on.
Gaming,
Forget
you know,
about it.
yeah, when gaming culture was more, how would you say, for the people, you know?
Yeah, but it was still kind of nerdy back even with G4.
Yeah.
But G4 actually was before. It was actually called something else before G4, I think. Even,
Yeah,
wasn't
Tech TV.
it? Tech TV.
Yeah,
he knows
dude.
the
Look,
history.
trust me, I was a huge fan, dude. I was like
Yeah.
representing the nerd culture. I was like, yeah, those guys are out there. I was like, huge fan of X-Play and shit.
Yeah, bro.
Yeah,
Adam Sessler,
Adam
Morgan
Sessler,
Webb.
Morgan Webb. Yeah, this guy knows. This
Yeah,
guy knows
man.
his shit.
I remember Adam Sessler was golden bald and he was still trying to be cool, spiking his hair up. I'm like, dude, it's a wrap.
Damn shots. Shots
and then Morgan
fired.
Webb was this hot girl gamer
Yeah,
with,
hot girl gamer. Yeah,
you know, the freaking muffin top body.
Yeah. Hey, I kind of had a crush on her. Not gonna
Did you?
lie. Yeah. I was like, okay, all right. She's kind of cute.
Yeah.
But then they got a way hotter one after her.
Yeah,
Olivia Munn, I think is her name.
she had.
Yeah.
Nah, that was Attack of the Show, bro.
Oh, okay.
You're mixing
Okay, I'm
shit
mixing
up.
it up.
But yeah. Attack of the
Yeah.
Show was also great.
Yeah.
Yeah,
I didn't really
was
watch it,
funny.
though.
I was all about the X-Play life.
I didn't. I watched X Play too, but then Attack of the Show came on the radar for me, and I was like, okay, fuck
And
yeah.
you enjoyed it?
Yeah.
Okay. I think I watched it a couple times, but I wasn't
Yeah.
a huge
Attack
Yeah.
of the Show guy.
Yeah, but now, now nerd culture's dead. Show is gone. Now it's all like, racist taking over gaming and stuff.
Racist?
Okay.
I think this is called squeakers who are edgy.
Sure,
Saying
yeah.
the N-word in chat.
Well, they call it the gamer word now because that's like their go-to.
What, the N-word?
Yeah. The gamer word.
Yeah.
Anyway, speaking of G things,
Yeah.
G related. Big G.
Big
Google.
G.
Big G, Google.
Oh, Google.
You know what
Oh,
I'm
I
talking
see.
about?
Yeah.
Big
yeah.
G, Google, man. The rainbow colored Google G.
Indeed.
Did you hear the news?
Yeah, I did. So
Are you sad?
why?
Because you have money in crypto?
So I wouldn't call that being sad because we could go into a little bit. So you're talking, of course, about the quantum supremacy.
Yes, let's preface this by saying, quantum, we're going to talk about, the main topic is going to be quantum supremacy.
Indeed.
Google officially made the announcement about a week ago, but
Yeah.
they've achieved quantum supremacy for a while. They've had it for a while, I think. They didn't
Really?
even know, there's this video that they published, and if you want, you can kind of put it in there. I don't know if it's up to you.
Is this the one you sent me?
I think so.
Okay.
Yeah. Where it was, they were just talking about, hey, we didn't even know we were like in the quantum supremacy
Realm.
regime. Yeah.
Okay.
Because they were, if you watch the video, they were mapping this line and saying, okay, if it's no longer linear, then we've achieved supremacy, and then they kind of thought it was something else, and so sure enough, they were like, okay, we're in that regime now, and so
Yeah, I think I saw that, but I thought they said that there was an error or something with their equipment.
that's I think that's what they thought. I watched it in passing and during my lunch break, and I was like, oh, well, cool.
Okay.
Yeah, it's like a 10-minute video or something, or 15
Probably
minute
shorter, actually.
Maybe it was.
Yeah.
I think it was called demonstrating quantum
Yeah.
supremacy or something.
Yeah. And so so for the people out there, what does that mean? Do you know what they mean by quantum supremacy?
Sure. Should I just give you the definition?
Yeah.
So basically, quantum supremacy is, to sum it up very easily, is when you've invented a quantum algorithm that can completely outperform a classical computer doing the same task.
Yeah.
So there's a little bit of contention with the word quantum supremacy. Like some people think that it's not really a good term because people don't think that quantum computers are ever going to be supreme over classical computers. Rather, they're going to live in conjunction.
I see.
They're going to live together in many respects, because quantum computers, a lot of times people think it's going to be like, oh, it's this whole computing architecture that's going to completely change classical computing. It's not really the case. Quantum computers are going to be used alongside classical computers.
I see.
They can perform certain calculations and do certain algorithms that can, do things like optimization, or they can do specific kind of tasks that won't be the same things that classical computers do. So supremacy is kind of a misleading word because it sounds like quantum will reign supreme over classical computers, which is not really the case according to most experts.
I see. So so you're saying there are only certain, like right now as it stands, there are only certain like maybe you could say problems that quantum computing can solve.
Yeah, exactly.
Over classical.
Yeah, exactly. So I'm sure I don't know if you're familiar with one, but there's the classic Shor's algorithm. Are you familiar with it?
No.
Okay, so the Shor's algorithm is kind of the one where you referenced me needing to sell my crypto.
Oh, okay.
This I believe, I may have to bite my tongue on this. I'm not sure exactly if it is the same algorithm, but the Shor's algorithm is the one that has to do with prime factorization. So this is what we base our RSA encryption, that would be like banking, any kind of major encryption schemes that we use,
like Wi-Fi, all that shit.
Yeah, like the encryption schemes on your
bank
computer
bank
for
encryption,
like HTTPS and all that stuff.
Yeah.
So that's the RSA encryption. That would be broken if you could create a quantum computer that could utilize Shor's algorithm, or that could perform Shor's algorithm. You could actually do that in you could factor those prime numbers in a reasonable amount of time. And right now we rely on those the slow speeds of classical computers to be able to secure our data or our banking information or anything and everything. So basically, it's like classical computers factoring prime numbers, large prime numbers, is a very hard task. So it takes the classical computer a long time to do it. Age of the universe.
Yeah.
So that kind of protects us from having our information broken or stolen or hacked.
Is that only because the way classical computers, I guess, process information? Would you say it's because, correct me if I'm wrong, but it's sort of a linear process, right?
Right. So with classical computers, you have to compute things one at a time, right? Of course, there's like parallelization with like GPUs and things and whatnot, right?
Or CPUs where they have multi-cores and shit.
Yeah. So like multiple threads and things. You can do a little bit more nowadays with the, the kind of advanced architectures we have available. But with a quantum computer, you have like a way larger number of parallelization, essentially, because, with quantum computers, each qubit that you add to the system, you're effectively, it's increasing.
The number that they throw out there is 2 to the n, right?
2 to the n, yeah.
Where n is the number of qubits?
Of qubits, exactly,
okay.
Yeah. So you increase by 2 to the n times, which is, a crazy amount. So once you start to get to the realm of like 50 qubits, or maybe I think they said like 300 qubits, it's like the age of the universe, or that's like more atoms in the universe or something they said.
Jeez.
Yeah. So I think it was something like with right now with I think well, never mind. I don't want to.
Okay,
I don't want to say numbers.
Don't throw numbers out there. Yeah. I mean, they're
I don't want to get roasted.
Yeah. They're huge. They're big players, right? Google's one of the big players in the quantum computing sector, right?
Yeah. So
and
Google,
then there's
go ahead.
No, and then just correct me if I'm wrong. There's D-Wave.
Yep.
I forget the name of the other one. Do you know?
Rigetti.
Okay. Are there any other ones? I think there were
IBM.
Oh, IBM, of course. Yeah.
Can't forget them.
Yeah. They're all sort of trying to. I know that they were all trying to build some quantum computer in some sense, and the architecture doesn't vary too differently, right? Because they all kind of use obviously some superconducting kind of high temperature superconductor. Right,
I'm not sure if it's high temperature, because I think I'm not sure honestly, but I know Google's
We'd have to look at the
computers-
white papers. Yeah.
Yeah, Google's
Yeah.
computer, it has to be cooled to 2 millikelvin or like 15 millikelvin.
Okay.
But I don't know if that's just because of the quantum or because of the superconductor, or if it's because of like to reduce thermal excitations or something.
Yeah.
So I don't know exactly.
Yeah. No, so yeah. Anyway,
But you were saying that the architectures are similar, which I don't think that's true, because
No?
in the case of D-Wave, I believe they call those computers quantum annealers.
the hell does that mean?
Yeah, I'm not sure. I know it's some kind of optimization. It does optimization stuff.
Yeah.
But if you remember, D-Wave was like
Annealers.
one of the first people to come on the map
Yeah.
with a quantum computer that was
Sold.
in the private sector. So I can't really speak on it because I didn't do any research on D-Wave.
Yeah, we'd have to compare white papers. We'd have to do like a full
Yeah.
dive into
Right.
that. But right now, I guess we're kind of giving a survey of what that means, like the scope of this sort of announcement, right? So
Sure.
this is like the first public announcement of reaching, quantum supremacy, as they say.
Yeah.
Yeah.
But of course, the quantum supremacy is even up for debate, not only just because the term is kind of vague.
Mm-hmm.
I think they call the lower form like quantum advancement or something.
Okay.
And IBM claims that Google actually did not achieve quantum supremacy.
Ooh, them's fighting words,
Yeah,
man.
exactly. So they came out quick. I think one of the main researchers on the quantum computing system for IBM did a bunch of research and claimed that the algorithm that Google claims to have done in, I think it was like they said 200 seconds,
Yeah.
comparing to the classical computer that was run in Oak Ridge.
Yeah.
They said that the Oak Ridge one would take 10,000 years. IBM claims that they just didn't do the right algorithm.
Ooh.
And it should really only take about 2.5 days for the supercomputer to do in Oak Ridge.
Ooh.
So they think that there's a little bit of like,
They're
there's a little
kind
bit of contention with the
BSing their
claim.
numbers a little bit. Would
Yeah.
you say? Yeah.
Yeah, there's a little bit of contention there. And
Yeah.
that's probably mainly because IBM is a direct competitor with Google.
Yeah.
And they're also trying to build a quantum computer to
Yeah.
achieve quantum supremacy as well.
Yeah, and bring it to market and
Yeah.
stuff. Yeah. That's huge. I mean, it would be huge, right? The implications are, you build this. By the way, reaching quantum supremacy will build whole new industries because you'll have quantum cryptography will have to be developed. Obviously, if you're a software engineer, you'll have to probably learn how to write algorithms in this new
Quantum.
architecture,
Mhm.
and then it's it's going to be kind of nuts.
Yeah, well, all that stuff is a little bit far in the future.
You think
Potentially, or
so?
maybe not far in the
But
future.
like, say if you were starting school now
Mhm.
as an undergraduate, I think I would say it's probably advisable to get into like quantum cryptography if you were doing like computer science, right?
Sure, it kind of looks more real in the landscape now.
Like 10 years from now, maybe this will be
Yeah.
lucrative.
Yeah, they kind of people have been comparing this quantum supremacy achievement by Google to like the Wright brothers' first test flight.
Oh, dang,
So,
that's huge.
Yeah, so they're saying like the thing is it's like you still don't really know how far we can take it because there's one thing that the guy who is in charge of this Google project with the quantum computer, his name is John Martinez. I think he's a professor at UCSB in California. He says that really the thing that you have to there's two kind of components that are important with quantum computing to achieve it, and that is quantity and quality of the qubit. So he says that some people have been focusing on just the quantity of qubits, and then some might be focusing on the quality. He says quality being the two most important, or the most important of the two features.
Okay.
And what I mean by that is, like when we hear with computing, we say like, oh, there's so many, well, let me just talk in terms of the quantum computer.
Sure.
The more qubits you have, the more computational
more processing power you have.
Yeah.
Yeah.
Like that's when you start to really get the big leaps in doing things more than a classical computer.
Yes.
But John Martinez says that the quantity is not the only factor that matters, and actually the quality of the qubit is is probably more important than the quantity.
And that
at
would
this
make
stage.
that would make sense to me intuitively as a physicist.
Okay.
Only because, correct me if I'm wrong, I think the quality of the qubit would mean the fundamental principle of this whole quantum computing algorithm thing is based on the quantum superposition of the qubit state, right?
Yes.
And so, you can,
And it's qubits.
qubits state. So
They're coupled.
the qubits have this wave function. You can look that up. You can Google it.
Mm-hmm.
That corresponds to, you can say, if the physical state of the system. Okay. And correct me if I'm wrong, but he's saying that the quality of this has to do with how long you can keep that system in that state.
Exactly, 100%.
Yeah, okay.
So essentially, it's exactly like you're saying. It's what they call it is the coherence times.
Yes.
So with the current computer that Google's developed, the Sycamore chip is really. I don't know if it's if the chip is just called Sycamore, or if the whole computer is. They call it the Sycamore processor.
I guess the
yeah,
chip.
but the computer itself is, I guess, they just all call it Sycamore.
It's a whole
That's all I
thing,
can find, yeah. So that one.
I mean, the
has-
computer is like. Have you seen the diagram?
Yeah,
It's
it
like
looks-
It's like a. It looks like one of those classic computers they had in the 70s where it's like water cooled and like this huge box. You know what I'm saying?
But it looks like a giant chandelier.
Yes, it does. But it's because they have to super cool it down to super low
Yeah.
temperatures and stuff.
Most of those tubes and curvy tubes and gold and everything, that's all for the cooling.
Yeah.
And then it's really just the tiny chip on
Exactly,
it. That's the
yeah.
whole quantum computer. So it's like you got all this junk on here just for that little chip.
Exactly.
So it just shows you how fragile that state is. And they have to be able to isolate this from sound, from heat.
Any kind of energy, right?
Yeah, any kind of energy that's going to interfere with these qubits.
Mm-hmm.
So the coherence times are the really key part right now into making quantum computers relevant and usable.
Mm-hmm.
So the longer coherence times you can achieve, the more likely you are to be able to develop a usable, workable quantum computer.
Mm-hmm.
So right now, the order I think of coherence time they have for this Sycamore quantum computer is like on the order of like 10 microseconds. So that's kind of, it's pretty short, but they can do these calculations over and over again and then, make an average of it and then kind of get the values that they want.
That's kind of cool because then obviously extending the lifetime of that calculation, because the calculation lasts as long as that coherence time, right?
Yeah.
So I guess that's what he means by like, you not only need the processing power, meaning the number of qubits, but you also need to have a good sort of coherence time. Yeah.
Yeah, because you need to reduce the error rate. So
with the error rate, that can you talk a little bit about that? What does that mean?
Yeah, so normal computing, we have this kind of thing called error correction.
Uh-huh.
And with classical computers, it's a little bit sorry. Yeah, I'm making noises with the microphone. But with classical computers, it's kind of easy to have a lot of error correction because when let's say if you have a computer sitting in your house right now, we're constantly being bombarded by cosmic rays and all kinds of crazy particles from the universe, from the space, right?
Yeah.
And like a stray muon could come into your PC and then it could knock one of your bits into a different state.
Uh-huh.
But of course, with a classical computer, that doesn't really matter because one bit is not going to really mess up your whole system.
Yeah.
Because all the bits are they're separate from each other.
Yeah.
The problem is with quantum computing is all these bits are intertwined. So when one bit gets messed up, it affects a ton of them.
Right. So it causes this sort of cascade effect.
Exactly.
Collapsing sort of.
Yeah, so it messes up the whole wave function. It changes everything.
Yeah.
So the coherence time is very difficult to achieve on a quantum computer because the state is so fragile. And error correction, you have to find a way to make it so that you can achieve some small percent of error and still get the calculation that you want.
I see.
So they're developing ways to do error correction on quantum computers, and that's kind of like really a major I guess I want to say a major part of developing usable quantum computers right now. That's a big area.
Dang, that's huge.
Yeah,
That's like a That's going to be $1 billion industry, probably $1 trillion industry pretty soon.
I don't know, man. It's going to be useful. I mean, they say already with this Google machine that they can already see an application just with this specialized algorithm that they developed for this this particular quantum supremacy demonstration. I don't know if I guess I should kind of mention that the algorithm they developed for this quantum supremacy is kind of a useless random circuit. It's not really used for any kind of real quantum computing
They didn't.
applications.
It's a sort of what do they call this in R&D? They say just like what's the word I'm looking for?
Maybe proof of concept or
Proof
something?
of concept.
Yeah.
Thank you.
Yeah, so it's just like a random circuit that they built, that they knew that they could build it easily. It uses like NOT gates. NOT gates, for people who are not familiar, a NOT gate is like a very easy circuit or logic gate to build, where it changes a 0 state to a 1 state, and then it changes a 1 state to a 0 state. And that's like one of the basic fundamental architectures for building computing systems. And anyway, what was I saying? So that random circuit that you build, they already can see some application for it because it can generate real random numbers.
Yeah.
So it's actually almost like they created a real random number generator now.
Damn.
And like before then, it's been
Impossible to make a random number generator.
Yeah.
everything's pseudo-random. So actually this already came out with something, and it's really just, when these kind of breakthroughs come about, you see more and more applications for these type of things that you may not have known.
Yeah.
And that's already one that they see is that can make random numbers now, truly random numbers.
Dang, the lottery is going to be
Yeah.
truly random now.
So these people winning twice in a row. The jig is up now.
Dude, that's insane.
Yeah.
How did you feel about the news?
About the quantum supremacy news?
Yeah, what did you think?
I mean, I'm happy for it, man. I always like to see technology, coming about, new technology. How about you? What did you think?
I was excited for the future.
Yeah.
Did you
Cause
sell your crypto?
no, I don't. I only have $100 in crypto, and that's
I think you were the first person I've ever known, Juan, who actually bought the quantum
crypto.
resistant crypto.
Quantum resistant crypto. Hell yeah! Shout out. I can't really, what is it called? Tampering? I'm not going to do tampering on here.
Yeah.
On this. Or the FTC or whatever will come after me. But yeah, it's I was one of the. Well, it's because I don't know. There are reports of this happening. Like there were kind of musings underground that okay, there's a company out there that probably has something related to it. But of course, like you're saying, it's a little bit. It's not. It doesn't really affect the mass market just yet, unless of course there's governments out there that are funding. Like sort of like maybe, unless there are governments out there like the
black projects or something.
Yeah, they're
Okay.
like the U.S. government or maybe some other governments out there might be funding some black projects, like you're saying, sort of hidden funding to get so they can have their own sort of quantum computer to do whatever they want.
Okay.
Meaning that they can break into anything and steal any information that they want. This is
Right.
huge. This is huge for intelligence agencies.
I kind of don't think so, though. I think because the major players in the quantum computing game are like the guys who are in universities,
private
and whatnot.
industry?
Yeah, I think it might be in universities and stuff. John Martinez he's a professor at UCSB.
yeah.
They have to pull him into Google just to be able to develop these things. I think it's too leading edge for a lot of these private industry guys. They don't really know enough how to build it. You need
Maybe so.
you need true physicists on these kind of projects.
Yeah. Maybe they did need proof of concept
Yeah.
kind of thing. Well, now, I mean, but this opens Pandora's box, right? So
Yeah.
the end goal now would be something like that. Maybe, you'd have to simultaneously build two paths where you have quantum cryptography and quantum, more quantum, building better quantum computers in a way.
Well, I've heard some things actually that some of the architectures that exist already are kind of quantum resistant. I
That's
think
what I've
elliptic
heard.
curves are kind of one of these ones that are safe. You just would need to increase like the number of whatever the hell the number of points that the curve passes. I don't want to get too much into elliptic curve fitting, but there are architectures I think that are apparently quantum resistant that exist today in some respects.
Okay.
I also reached out to Vitalik Buterin, who's the inventor of Ethereum, on Twitter, and I asked him
Yeah.
if the quantum supremacy is going to ruin my ether, and he said no. So
Yeah.
that made me feel a little bit better.
No, I don't think. I don't think if you own crypto, I don't think you're at risk.
No.
At least not yet. I mean, there are talks. I monitored right afterwards. I monitored the big crypto players like Bitcoin and stuff,
Yeah.
and see what the price did.
Yeah,
Because that
it
reflects.
actually went up.
Yeah,
Crypto went up like 19% like a
Yeah.
couple days ago,
because that reflects.
or at least Bitcoin did.
Right, that reflects how the market or how the people see what's going to happen. Because if
Threat.
people dumped it.
Yeah, then you would be more worried.
Yeah. But I mean, I think it'll be fine. Everybody talks about, stuff like this being quantum resistant, and I'm sure that the same thing. Like our banks are probably, hopefully, working on some kind of, way to be prepared for the inevitable, sort of. But I mean,
I'm sure they are.
Yeah.
They got to be kind of, because that would crumble their whole business if that was
Yeah.
the case.
yeah, but this is huge, man. This is because can you imagine if government achieved quantum supremacy? If they achieved like
Like a real one.
a real one, this would be like somebody having a nuclear weapon
I
almost.
think it would, man.
Yeah.
I think it's one of those revolutionary technologies where now, let's imagine if the U.S. got quantum computers. Like we could literally hack into any nation's
Oh, yeah.
infrastructure within
Man.
a reasonable time frame. Yeah, and see all their secrets,
Yeah,
So that would be crazy.
that would be insane.
Yeah, that'd be
And
next level.
yeah, that's what I mean. It would be like having a bomb, having a
Yeah.
knowledge bomb in a way.
And we are in kind of like the age of like tech wars,
Yes.
Because like China will hack us and things, and
Mhm.
South Korea or North Korea even too. Not South Korea, it's North Korea.
Yeah.
Russia, everybody
Mhm.
does cyber attacks now.
Yeah.
So we're definitely in that age of tech war.
Yeah. The next 50
Cyber war.
years, I know. The next 50 years, we're about almost 30 years old.
I
know,
am
plus
already
minus.
30 years.
Plus
31.
minus, plus minus 2 years. We're about 30 years old.
Yeah.
And so the next, if we live up to be 80, man, the next 50 years are going to be
Interesting.
very interesting.
I'm ready for self-driving vehicles. Really,
Well, that's the
next
number
one I
one
wanna
thing.
see,
Yeah. Because that's the number one thing that kills people, I think, nowadays.
Yeah, like
I've
car
known
accidents?
a lot of people that have passed away from car accidents.
really.
Yeah, like I'm just like, man, this is like we're still dying out here. Like, well, I think more Americans die on the road
Mm-hmm.
than any other thing. Like more than obviously guns, but
Yeah,
like that's like the number
like
one.
it's hundreds of thousands, isn't it?
Dude, at that, I would say if I pulled a number up now, it'd probably like over or under. What do you think? Deaths a day.
A day,
A day. I'm gonna say at least
like 10,000, maybe.
10,000.
Maybe not 10,000. I don't know. I'm not really
Okay,
sure.
because when I drive on the road, I know this is a little bit of a tangent here,
Okay.
but back in Texas, if I'm driving on the road, they would have these signs that say, 16,000 deaths 1,600 deaths this year.
yeah,
Drive safe, and it's like barely July or something.
Okay. Yeah.
So if I take Texas,
extrapolate that, double it, maybe.
extrapolate it, yeah, because Texas is probably the biggest state.
Right.
Multiply that by,
So you're thinking
I'm thinking 5,000
5,000 a day?
Yeah.
Okay.
a year.
A year?
Yeah,
For just the one state though.
yeah.
I'm saying for the nation.
For the nation, multiply that by 50.
Yeah. Yeah. I think
Nah,
you're right.
maybe less.
Maybe
Maybe less. Maybe less than that.
Tens of thousands though, certainly.
Certainly. That's a lot,
It's
though.
way too much.
It's way too much.
Yeah.
And that's why I think cars are going to be the next self-driving vehicles are going to be.
I mean, they're already in existence. They already could probably do it if
Yeah.
there were more actual vehicles that are self-driving.
Yeah, have you had anybody resisting it? Have you talked to people about it?
Oh yeah, tons. I have lots of people tell me I don't even understand the argument. They're just like,
I don't either.
They always say like, I want to drive my car. I don't want self-driving cars. Or they'll say like, I don't trust a machine to make the choice for me. And I hear it a lot. I'm just like
Me too.
so shocked by it. I'm like,
Me
you
too,
really
man.
think that a machine that can do calculations in milliseconds or even microseconds
Right.
is going to be worse than a human's response time? Like our response time is like seconds,
yes.
if that.
If that.
Yeah.
And yeah. And even then, people don't like to admit. I see this all the time. People driving with their. I mean,
Yeah, don't you want to
everyone's
text and
distracted.
drive?
People, people. Don't you want to just watch a video or something, or
go to sleep,
or
you
go to
know?
sleep, or read a book, or you'll have more time on your hands to
Right.
do whatever you want.
Imagine going on a road trip and you can just play video games while you're just sitting in the car.
You're just a passenger.
Yeah, that'd be so good.
That'd be
man.
amazing.
But anyway, we're kind of on a tangent.
Anyway, Google, make that
Yeah.
happen with your quantum computers. I don't know how, but
do you think? What do you think the future would be like? Let's say long term. Do you think we
Yeah.
could ever get quantum computers downsized to like, let's say, like smartphone level? Could you see it happening?
I'll give it at least 200 years.
Yeah, I think
At least 200 years.
It's going to be out of our lifetime, I'm sure.
It's going to need, it's definitely that. I think what's going to need to happen is physicists are going to have to figure out room temperature, if not close to room temperature superconductivity to reach that, because you would need to isolate your system energetically
Yeah.
to even get that to be at the level that we need it to be.
Right.
If not your phone, maybe at least your desktop PC within 100 years, I think. Because, I mean, look at the scale of computers, how fast they've grown
Yeah.
in the past 30 years, 40 years.
True.
Extrapolate that, right? It's just, I would say at least 100 years for quantum computers to be like your PC at home, and then maybe 200 to be in your pocket.
Okay. Wow.
Maybe. At
Yeah,
least.
I can see it.
At least.
I think it's going to be out of our lifetime, though.
For sure.
I'm pissed.
Sad. Damn you, kids. If you're watching this now in the future, just...
Yeah, I wish I could just
I
see
hate
the
you. You guys are
technology.
so lucky. I know. That's really what drives me from being alive. A lot of the time, I'm like, damn, the future is going to be amazing.
Yeah, man. The technology it just is really impressive to see what changes that come about.
Yeah.
Especially when they're big changes like the internet. Like we got to actually live through the internet.
Yeah.
Which is just so cool.
I know we're at that cusp, especially or us, the last generation that knew what it was like to have pre-internet and post-internet.
Just such a different world.
Yeah, you kind of live in two worlds in a sense.
Yeah.
It's kind of weird because,
Such a simpler time, in the 90s.
It kind of, there's a little bit of nostalgia there. But then again, I don't know if it's our generation that's going to be kind of leading this movement of what is digital hygiene, in a sense, where it's like we need to be careful about our digital consumption and like how that affects our own mental health and stuff, right?
Yeah.
Just looking at screens and all the time and isolation and what that means. Because, I mean, we're social creatures, right?
Mm-hmm.
And maybe like psychologists or sociologists will see a correlation between like, isolation and digital, like, because this is digital isolationism. You have a thing that communicates you socially, but you don't have any human to human interaction. You know what I mean?
Yeah.
And
Well,
I don't know if those interaction things are one-to-one with physical interactions.
yeah.
You know what I'm saying?
Like something's missing from it.
Yeah, I think there might be something there that
I think you're right.
maybe this is up to sociologists to figure out. But I think they're, and we're going to be the one group that they're going to study because we're at the cusp,
Mm-hmm.
and they're going to be like, how do they compare versus
Yeah.
the people that are just born into the internet age?
Yeah.
I think our generation definitely sees an issue with the
Media.
amount of connectivity that we have.
Yeah.
Like us, we have this weird mix where we kind of, at least for me, like I try to stay away from some social media platforms.
Yeah.
And I've only recently got into it just because, trying to promote the podcast and
Yeah,
everything.
yeah,
I
yeah.
didn't even have Twitter until this year.
Yeah.
I didn't have Instagram or any of that stuff.
Yeah, I didn't know what YouTube was. No, I'm just kidding. No, I'm just kidding.
I was gonna say.
Nah. It's it's nuts. Yeah.
Yeah, man.
What are your final thoughts on that quantum
Supremacy.
supremacy? Yeah.
So, I think it's a very important achievement, and I think it's gonna probably inspire a lot more innovation, because now it's like the proof of concept has been shown. There's no like, it showed that there's no real like roadblocks of physics to develop an algorithm that is going to be faster than a classical algorithm. Maybe if it's not supreme, like maybe if it's not like because IBM's claiming that the 10,000 years is an exaggeration, and it's only 2.5 days for the classical algorithm. Of course, with these kind of things, that's just an initial thought.
Yeah.
If they optimize it more and more, they could make it less and less time for the classical algorithm, and then it's actually the same amount of time for the classical algorithm to perform as a quantum one. Mm-hmm. So we still kind of wait and see.
Yeah.
But if the quantum computer even has any kind of speed up compared to the classical one, that is a very important proof of concept, because now we've actually demonstrated a true algorithm experimentally that can be solved quantum mechanically that's faster than a classical computer.
Yeah. So can we tell people before we leave a little bit about what research fields go into this particular project that you can sort of like speculate on, like what disciplines go into working in a project like this, do you think?
For quantum?
For this building
this
a quantum
particular
computer.
One? Yeah. So of course I think this is condensed matter.
100%.
This is the condensed matter field. With condensed matter, it's probably like a bunch of stuff we do is related to computing.
Yeah.
Like that's why I got into condensed matter, because I was interested in the computing side, the fundamentals of computing.
Yeah. And by that you mean like you mean processing the materials or finding the right materials to build a computer
everything.
from?
I mean, the
so
materials.
let's expand on that, like for the audience here.
Yeah, so the condensed matter physicists, the guys that invented the transistor.
Mm-hmm.
So like just knowing logic operations, that's condensed matter.
Mm-hmm.
The materials, let me think what else.
Like a lot of the engineering came after, you would say, right? Like a lot of these guys build proof of concept devices in a way.
Yeah.
And then the engineering came
later
as an afterthought.
Yeah.
Like, oh, we have to make it like this.
Yeah. And that's kind of physics in a nutshell anyway.
Sure.
It's like the physicists invent the fundamental proof of concept, kind of the rough prototype.
Yeah.
And then the engineers actually take it the next level and optimize it and make it manufacturable and then consumer ready.
Yeah.
So yeah, I mean,
so engineers, and then physicists, of course, condensed matter physicists, and then one off the bat, computer scientists, probably,
computer
right?
Scientists is a big one. They've kind of done a lot more work so far though than the experimentalists, because the algorithms have been slowly but surely made more and more optimized for these quantum schemes. I think it started with the quantum algorithms were taking exponential time to complete.
Yeah.
And then they finally got it down to like the quickest algorithm, I think, was like some polynomial to like the 2.67 or something.
Sure. Yeah.
So it's like almost a square, a little more than a square polynomial.
Yeah.
And that was over the course of several iterations. So the computer science people are a little bit ahead of the game.
Yeah.
But yeah, it takes all these fields.
Yeah.
Mathematicians even too, because like, I guess mathematician or like theoretical computer science, because they've got the whole thing with polynomial time. If you've heard of big O notation.
No.
So big O notation is how they characterize the time it takes for an algorithm to run.
I see, yeah.
So it's the polynomial versus exponential time.
So they do need some data modeling kind of.
Yeah.
I imagine you would have, maybe they would bring in a mathematician or two.
Yeah, it could be either a mathematician or a computer scientist.
Or use a good physicist, a good theoretical physicist.
Yeah, it's like it kind of crosses all three of those regimes pretty nicely.
Yeah, so
you got the whole P equals NP problem and all that stuff that can go in there. We don't want to get into that too much, but that's basically just means polynomial versus non-polynomial time algorithms. Are they equal to each other or not?
Yeah. So in case you want to think about careers in this, those are the three interdisciplinary fields that you can probably go into, say, if you want to do quantum computing in some way, right?
Yeah, if you want to go heavy theoretical, you can go math. Actually, you can go either one of those.
Yeah, theoretical physics or, mathematical physics.
Yeah.
Or
mathematical or theoretical like computer science.
Yeah.
And then if you want to go more at the ground level, then you go experimental physics, engineering, computer science if you want to do the actual software.
Yeah.
Mathematics, maybe not so much you can do with like ground level, but maybe you can do applied mathematics. I'm not sure.
Yeah. They might need you to build models and
make
sure some figure out how to make things converge, because I imagine they're going to have a lot of infinities with stuff like this. I'd imagine that they would have, when they're building an algorithm, they would have a shit ton of things that are just kind of all over the place.
Yeah, I'm sure there's a lot of theory work that could be done. Yeah.
So if you're planning on doing it, then these are the things that you might want to look into, because this is, and I would say 10, 20 years is going to be, it's going to be pretty huge. Like, because I mean, it took, if you look at something like an experimental condensed matter, right? You see 2D materials, two-dimensional materials that started happening. I mean, they were discovered a while back, maybe 40 years ago, but you know, with graphene, it was kind of hot in the early 2000s.
Yeah.
Yeah, like and just now it's getting to the point where people are like thinking about applying it to certain things. So
yeah, kind of have that resurgence with those magic angles.
Yeah, that stuff. Yeah. So yeah, just now it's just 20 years later, it's being implemented into like chips and stuff. So
okay, is graphene actually being implemented now?
I think so. I think in some applications.
Okay,
I'll say that.
But they still haven't found a way to mass manufacture it, have they?
I don't know. I'd imagine they do, but it's about what you're trying to do, I think.
Okay.
I imagine it's very specific problems that you're trying to solve.
Well, let's say for now we don't know.
Yeah, let's say for now we're speculating.
I don't think you did either.
No, I'm speculating.
Okay.
I'm speculating. But anyway, I'm giving it 20 years for this to be really like pop off. And yeah, it's cool.
Yeah. Quantum stuff is definitely looks like it's real now.
Oh, one more thing.
Yeah.
When reading this, did you walk away with some better understanding of kind of maybe a physical sense of quantum mechanics, because how you're reading about how they apply it?
I did. I finally, because I've been trying to figure out what the hell superposition was. Like, how do you actually put something in superposition for a long time? And it just seems that most things are already in superposition. It's just as soon as you measure it, once you measure it, it's now a collapsed state. Yeah. But then once you let it go, it goes back into superposition after a certain time
evolution
frame.
Is what they call it.
But then it's also like, the fact is, you can also then say, like, why did things get coupled together? And that one I'm not really too sure just yet.
I think it has to do with like isolating, but this is why they take it to low temperatures, right? They try to isolate it energetically. Yeah, the system.
But the thing is, like, okay, so with the quantum Sycamore computer that we're talking about here, it's got an array of like 54 qubits. I think one of them doesn't work, and one qubit. So they use these cross transmon superconductors.
Okay.
So it's in a shape of a cross. So each of those cross tips or vertices, I guess you could say, is connected to another qubit, essentially. Oh. Well, it's actually connected to some kind of coupler. Yeah. And then the coupler connects to another qubit. So you can adjust the couplers to be able to send it some kind of microwave signal frequency between 0 and, like, I don't know, some amount of megahertz. Yeah. And with those different ranges that you can set the coupler to, you can couple those different qubits to each other in a different amount of ways. Interesting. So what that means, though, is still a little bit hazy for me. Yeah. I know that I kind of get more how to put a particle in certain states now. Yeah. Because the example that John Martinez gave, I looked at one of his videos, was imagine if you have one qubit, right? Yeah. So the qubit 0 state is the ground state of, let's say, of a hydrogen atom. Yeah. The 1 state would be some excited state. Yes. The way you excite the excited state, or excite the ground state to an excited state, is to actually send some kind of microwave frequency to that ground state.
Basically something with energy, some like a photon. Photons are, in this case, are microwaves.
Right. So they say microwave, I think, because that's the resonance frequency that they have for that particle.
This particle, yeah.
I don't even know if it's a proton. It might be something else. Sure. But you can send that frequency, resonant frequency, and it will give it a 1 state. Yes. But then let's say that frequency is like 40 megahertz. Yeah. Now, if you half that, let's say you half that frequency, you send 20 megahertz instead. When you shoot a photon at that ground state now at 20 megahertz, it could either be in the 0 ground state or the 1 excited state. So you don't know which state it's going to be. And as you adjust that microwave frequency, that photon that you send to it, you can actually put it in a different state, a different probability state. And that's how you kind of navigate the block sphere. I think I'm kind of getting a little bit complicated.
No, I mean, it's illuminating to me, but this is sort of an appendix. This is sort of the appendix of the video, I would say.
Okay. But you can kind of set it in a different amount of states that way.
Yeah.
So let's imagine that you that your state is a 0 and a 1 state with some kind of constant or some kind of coefficient attached to those two states. So let's say it's 0 plus 1.
Yeah.
And each of those states has an A coefficient for 0 and then a B coefficient for 1.
Right.
You can adjust A and B's coefficient by adjusting that microwave frequency that you shoot onto that proton.
Very cool.
That's how you make the different kind of states.
Yeah. That's awesome.
Yeah. And then when you couple it, it becomes more complex, and then you actually have more and more of those states.
Yeah, like in quantum mechanics, they have, if you have like if you open up those other states, you're creating, I imagine they're saying that they have now the state it's combined with all those other states. So the linear combination of the other states.
Yeah. That's how
with
you
all
get
different
the real
weights.
power of the computation as well.
That's cool.
When you have all those states entangled with one another and you make this bigger and bigger wave function, that's when you actually get the ability to make all these huge calculations, because when the quantum computer actually goes to solve the problem, it gives you back a probability for each of those states.
Yeah.
And
that's
then that
cool.
can be utilized to actually do computations.
So were you able to appreciate your level of quantum mechanics knowledge to kind of seeing it and applied to something, right? It's really cool.
It was kind of useful. I feel like I'm finally understanding it now.
I think there needs to be more demonstration of this, like
in graduate school, you mean?
Yeah, like how it's applied, because these concepts are so esoteric and they seem, I mean, they're unreal to us, right? But if you see it applied, it's like, oh crap, it's like,
right. I kind of was thinking of a comparison to that. It's kind of like being told how to play a game, but then never playing the game.
Okay. So like if somebody told you how to play cards or something, right? Like Texas Hold'em, right?
Sure. Maybe? Yeah. Like imagine somebody trying to explain poker to you, but then you never get to play poker. So you can learn all the theory to it maybe, but if you never play the game, it's going to be harder for you to actually remember the rules and the intricacies of it if you don't actually play the game. Yeah. But I guess the more you read on it, like I just have to keep reading and reading and reading. Eventually you can know the book so well that maybe you can actually play the game. Yeah. But I think it's a lot easier when you play Texas Hold'em and know the rules at the same time, because then you actually can remember and retain your information much faster. Yeah. And easier, and you have more longevity to your information retention. Yeah, so maybe in 100 years, when they have classroom quantum computers, they can do these quantum tests in the classroom. Well, you know what I think they should just do? They should just make a simplified version. A toy model? Yeah, so the thing is, the best way to explain quantum mechanics is to just think of it as, don't even think of it in the sense of like normal physics. Mm-hmm. Just think of it like a game, like a Sudoku game or something. Mm-hmm. Like if you're trying to learn how to play Sudoku, you just need to know the rules of how to play it. Yeah. Don't try to attach your understanding of what you think about reality, about classical or Newtonian reality to it. That's a mistake that everyone does. It's a mistake I've done. And that's a mistake that, tons of people
Pretty sure
do.
Everybody, yeah. Yeah. Pretty sure even Feynman and Einstein.
Yeah, because classical physics makes so much sense and it's so logical. You're like, surely this just must continue. But no, it's like a whole nother game now. It's like learning a whole nother game. It's like you've been playing checkers all your life, but now you're trying to apply the rules for checkers onto chess. Yeah. It doesn't work like that. So you need to just learn chess independently of checkers. Yeah. That's a great analogy. They're on the same board maybe, but they're different games in a sense. That's a great analogy. Yeah. Yeah. So I think if we just learned, if we like gamified quantum mechanics, I think it'd be a lot better. I think in a sense it is, but you're right. Framing it in a way where, the mathematical framework
is a set of rules.
It is.
It's a set of gaming
But I think it should be
rules.
presented in a more clear picture like
Sure.
that.
Yeah.
Because I actually saw a really nice explanation about this with one guy. I think he's at MIT. He actually just explained quantum mechanics and the weirdness of it using instead of like momentum and position, he would use color and hardness.
I've seen this video.
Yeah, it was really a nice explanation.
He puts it through a filter. Yeah,
you got it. You got it.
Yeah,
it's much clearer to understand when you think of it like a game.
Yeah.
Because you're learning the rules of a game, and it kind of distracts you from trying to actually put those rules onto reality.
Yes.
That's always the problem with people doing quantum mechanics. You're trying to
Yeah.
fit it into your framework of classical mechanics that you already have.
Yeah.
Just don't even do that. Detach yourself completely.
Yeah.
Then you can do that.
Yeah. That's awesome, man.
Yeah.
I'm so glad to hear this from you, because I was like, I think now because I feel like I had to do so much reading for this one project that I had, talking about one of my senior projects for my undergraduate. It was reading about all this quantum stuff. And I remember coming upon that video at MIT and then a couple other things, and then reading through a bunch of stuff, and it really cleaned out a lot of my thinking. But I reached that point where I didn't know how to put it into words like you did so succinctly. But yeah, it's like a set of rules. You have to kind of sort of think of it independently of classical mechanics.
Right.
And
classical mechanics is a set of rules too, but they're just so
It
linked into our DNA.
It validates your experience, right?
Yeah.
Yeah.
It's like we're born knowing the rules already.
Yeah.
So it doesn't feel like a game.
Yeah.
But classical mechanics is a game too. It's just that we happen to be born into that game. We've been playing classical mechanics all our lives.
Yeah.
So we've gotten too good at it. We're trying to see everything in that light. Just doesn't work.
Yeah.
So I think that's how a lot of times you got to approach new physics. You just got to think of it as a game with rules. Just know the rules.
Yeah. 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 So, bam! What a perfect way to end it. I think.
You think that's good.
Yeah. Yeah. That's
I think
good.
We're at 52 minutes, so that's probably enough.
All right. So,
All right.
yeah, we'll stick for the outro.
Oh wait, what should we should leave a question though? What's
Oh,
a
yeah.
good question you think?
I didn't come up with one.
I would say what it so. I guess what does that make you think? Do you think Google actually has achieved quantum supremacy? You can probably do your own research on this if you want, and then comment on it. If you've done some research beforehand, leave an answer. But also, if you liked Terence's like kind of guide or approach to quantum mechanics, let us know, because I actually wanted to kind of, maybe I can make a blog post or something, or like kind of, I was working on this kind of thing, like quantum mechanics for dummies kind of thing.
That's the one you send me.
Yeah. Introduction and in a way, not introduction, but sort of how to talk about quantum mechanics.
Yeah.
And I tried explaining it as something that we can relate to with intrinsically with probabilities and stuff as a deck of cards, but we can talk about that later. But basically, what did you think about his explanation? Is quantum mechanics still kind of weird to you? And yeah, I don't know.
You got to do the math for quantum.
Unfortunately, if you don't like it.
I'd love to see in the future like a game for quantum mechanics where they just, maybe it's not actually quantum mechanics, it's just the rules of quantum mechanics made into a game. And that
would be amazing.
Yeah, and it kind of just makes it so it's detached from like an actual explanation for quantum, but the rules of that game
follow the
same rules as a quantum game would.
That would be
just
an awesome
like the MIT
game.
guys color and hardness features for his
let's end this video
particle.
now, because I have a great idea. Multi-million-dollar idea. All right. All right.
Turn it off.
Yeah, turn it off. All right, y'all. Stick around for the outro. Hey.
What's up, guys?
Thank you for making it to the outro. Crunk here.
Captain Picard.
Yes. Yeah. Want to thank you. I'm trying to do a voice. Let me get into it. Let me get into it. Right. The outro. The outro for Eigenbros. No, I can't do it. Sorry.
It's a good try.
Yeah, but we hope you enjoyed this episode. It was a lot of fun to kind of talk about just what quantum supremacy means for us, Google, society, and some other things, I guess.
Yeah. Hopefully it was educational, guys.
Yeah.
But yeah, just make sure to subscribe, comment, like, share, all that good stuff.
Yeah.
And check out the Twitter at Eigenbros and then Eigenbros.com. And we'll see you next time, guys.
Yeah, and comment on our costumes.
Yeah. Tell us what you think.
Yeah, see ya.
See you guys.